Hey folks, for this last video of 7.2, that should say 7.2, not 7.3, what I wanted to do for the problems was to actually present one of my favorite problems from this unit and go through it. And so I have a printed problem instead of a handwritten note sheet. And this video is probably going to be long because after this problem's over, there's another one that deals with some other topics. So feel free to skip around this video. One way to approach this is to use this sheet as practice and then skim through the video to see how you got it, how you did. So here's what's going to happen. For each part of this problem, I'm going to narrate my understanding, and then I'm going to draw the graphs for each section, and then move on. So if you, again, wanted to pause the video at various points and try and do this yourself and then check your answers, you are welcome to do that. So basically we have a scenario where there's a mass on a spring and there's a pendulum, and there's variables that are the same between the two of them. So the mass at the end of the spring is the same as the mass at the end of the pendulum. The spring, the mass is moved up a distance d and then released and allowed to oscillate, whereas the pendulum bob is moved horizontally a distance d and then allowed to oscillate after that. It doesn't say it, but they kind of imagine later on that the spring and the pendulum are the same resting length, and at the very least they start at similar distances from the floor. Now each graph here looks at the height above the ground versus time as they're allowed to oscillate. And so every graph has two curves on it, one dotted and one solid. And so the first question is, which line represents the mass attached to the spring? And briefly justify your answer. So we have what looks like this dotted line has a very small amplitude. It's always about the same height from the ceiling, from the floors rather, whereas this solid line has a much larger amplitude. It goes up and down further. And so for that reason, this solid line has to be the spring. So I'm going to start by color coding the things that I do on the graphs. So the dotted line is going to be the pendulum. And I'm going to put that in green on this worksheet. And the solid line is going to be the spring, and I'm going to put that in red. My apologies to anyone who is red, green colorblind. These are the two colors that I had access to right now. So what's my rationale? The spring moves up and down with a greater amplitude, because when you pull the pendulum to the side, it does raise it up a little bit, but not as much as just lifting it vertically. All right, next question. They repeat the trial, but they increase the value of d. So d is the distance that the spring is lifted vertically. It's also the distance that the pendulum is pulled horizontally, and then they release it. So now we're plotting new lines for both of those. So we're going to do the pendulum first. The pendulum is on a string, and that string doesn't stretch. So the lowest point that the pendulum reaches is going to stay the same. The only difference is the highest point that the pendulum reaches is going to get a little bit bigger. So for the pendulum, the only thing that's going to change is that starting height. So when I draw my new graph, I'm going to keep every feature the same except that maximum height above the ground. And so I'm doing an increasingly poor job at drawing that, but everything else is the same. So the pendulum has a higher, greater amplitude, and the way that shakes out is it has a greater starting height, but the same ending height. Now for the spring, the way amplitude works for the spring is the further it's raised up, the further down it's going to go as well. So for the spring, I'm both going to start higher and end lower. And that needs to be symmetrical. So the way I'm going to draw my graph is I'm going to start it one notch higher, so 1 meter higher, which is kind of ridiculous, and then end it 1 meter lower, and everything else is going to be the same. So I'm going to draw kind of a rough version of that. I could be a lot more careful, but I just have a greater amplitude. So greater amplitude for both. And I haven't talked about some other things that we are now going to talk about for this next one. In this third trial, they used the original value of D, but they increased the value of M. And so I'm going to have to manage what happens when we change the mass at the end of each oscillator. Now, the first one is easy because a pendulum, the period of a pendulum is 2 pi square root of the length over G. That means that the pendulum is not going to change at all. So I have to focus my efforts here on the spring. The period of a spring is 2 pi root m over k. So we are going to have a longer period, but that's not the only thing that's going to change, because when you change the mass, you change the force of gravity on that mass. And so that equilibrium position, where the spring force is equal to the force of gravity, is going to shift down. Because if this block weighs more, the spring is going to have to stretch more to make the net force 0 again. So the addition of that mass is you have a lower equilibrium point. So for the spring, this ends up, I think, being the hardest question to answer. We have to make a longer period and we have to make a lower equilibrium. Now on the graph, we're going to start, the distance d is the same, so we have to start it at that 8 meter mark, but I have to make both a longer period and a lower equilibrium. So this first one went from 8 to 4 meters, so that's an amplitude of 2, so I'm going to make it an amplitude of, let's go from 8 to 2, so we'll make it an amplitude of 3. So if I go from 8 to 2 and also make a longer period, then maybe I'm going to have this be one of the points that I use. And if it takes 0.8 seconds to get down, it's going to take another 0.8 seconds to get back up. And so I can very roughly draw a new curve for that spring. And that accomplishes a new equilibrium point. It used to be at 6 meters. Now it's at 5 meters and a longer period. All right, next one. This is the last one for this. Now they repeat it for a force trial. The spring is now longer and the rope is now longer. So if I go back to that picture, the spring is longer, the rope is longer. So that's going to cause some additional changes here. So we're going to start with the pendulum. The pendulum's like kind of hard to draw, but the pendulum, as we saw, the period does depend on length. So for the pendulum, we need to have a larger value of period, and because the string is longer, it's now lower. So we're no longer releasing it from 7.5 meters. Maybe we're going to release it from like 3.5 meters. We have to make a longer period, and so I'm going to try and make this about the same amplitude and a longer period. Technically speaking, the amplitude would be even smaller, because if the string is longer, moving at that same distance to the side wouldn't raise it up as much. It's like you're tracing out a much larger circle, so you don't get higher. So I'm going to just kind of estimate here, right? Like half a cycle for the pendulum used to be like 0.15 seconds. I'm going to try and make it 0.40 seconds. And so that means 0.80 seconds is one cycle. And so we're going to oscillate the pendulum like this. Oops, I messed up that dot. Okay, so that's our pendulum, and that's a very small amplitude, very large period, and it's shifted a lot lower. All right, for the spring is only going to be lower. Nothing else is going to change, because it's still going to stretch the same amount, because it's got the same mass on it. It's still going to have the same period, so I'm only going to shift things down. I'm going to shift them down like 2 meters. Just because that's easy for me to do. So I just do my best at drawing the same curve for the spring, just shifted down. So no other change. All right, now we're going to move into the last problem. Now this one is fairly tricky, and it's from an old AP exam, and it has to do with a collision. And so I wanted to cover a collision because we've talked about momentum a lot lately, and we talked about it a lot at the beginning of the semester. And so I wanted to remind you that even in this unit, we can still have collisions and momentum concerns. So basically we have this block M is oscillating on a spring. So block of mass M, it's block P, and then block Q is dropped directly on it. Block Q has twice the mass as block P, and they continue to oscillate. Now there's no friction on the floor, but there's considerable friction between the blocks, and so they're going to stick together right away. I'm looking for two things: the ratio of the amplitudes before and after, and the ratio of the periods before and after. So in order to do that, I think I'll just do the periods first because it's kind of easy. That collision is going to change the period of oscillation because the mass of the system has changed. Now, what's nice about this period equation is that the only concern you have when thinking about period is mass and spring constant. So I'm going to set up a fraction. On the top, I'm going to have the period expression after block Q is added, and on the bottom I'll have the expression before block Q is added. Now, once block Q is added, the mass of the system is 3m, and before block Q is added, the mass of the system is just m. And so, you can take your time working with this fraction, but the only difference between these two fractions is the presence of a 3 in the numerator expression for mass. Everything else will cancel, and so that means that the ratio of these two periods is √3. That's the only difference. Okay, now for the amplitudes, there's a lot more work ahead of us because the amplitude depends on the energy, and we have a collision. That collision is going to reduce the maximum energy available to the system because it's an inelastic collision. So we're going to apply conservation of linear momentum to this system. The initial system has block M moving, or a block of mass M moving through equilibrium. Well, at equilibrium, it is moving at the maximum velocity possible for that system. Now, when that collision happens, a block of 2m collides with the block of m, and they have some final velocity. So I can use this to keep track of the new maximum velocity of that system. So I have m Vmax equals 3m Vf, and if I solve that equation, I get the final velocity after that collision is equal to whatever the maximum velocity was divided by 3. So that's an important result. That new maximum velocity is 1/3 of what it was. Now, I can apply conservation of mechanical energy, because if I want to know what the new amplitude is, I have to see how this new kinetic energy maximum relates to the old kinetic energy maximum. Now, this is going to be before that collision. So I'm going to write this out as the maximums. So the potential energy is elastic, and it's based on the amplitude. And then the kinetic energy is based on the maximum speed. And so what I can do is I can solve and get a generic expression for amplitude. These 1/2s cancel, and so I get the square root of m Vmax squared over k. And now I'm going to take that and derive an expression for that ratio. So this is just generic. If I want to do a ratio of the amplitudes, I want to do that same thing I did for period and make two expressions, one on top of the other. So square root of. All right, so the sorry about the blip. I just realized I did the next part of the problem wrong in my rehearsal notes. So the amplitude of the 2-block system, so that's their mass. Their total mass is 3m times the maximum velocity that they have, which is v max over 3 over k. And then the amplitude when just block P was there is going to be the square root of m v max squared over k. So that one I want to clean that one up just a little bit. So APQ over AP. Now again, you'll see that like a bunch of things will cancel, and I'm going to do that cancellation now. So in the numerator, literally everything cancels. So it's the square root of 1. In the numerator, the things that don't cancel are 3 times 1/3 squared. And so 1/3 squared is 1/9. 3 times 1/9 is 1/3. And so the ratio between these two amplitudes is the square root of 1/3. And so these are like trickier problems for sure, knowing that you need to apply conservation of momentum to figure out amplitude because the total energy has been lost. All right, thanks for your patience with this long video, and you are now good to go for Unit 7.